In Chapter 3, we're going to spend our time talking about stoichiometry, and stoichiometry really is the study of how much that we're going to make, or how much do we need to make something. And so we look at balanced chemical equations, and we really need to translate what happens in a balanced chemical equation into the laboratory to figure out how much we need to weigh out to make the amount of product that we need. And so in this particular chapter, we're going to focus on mass and formula and reactions and all the quintessential chemistry that you probably think about when someone says chemistry. So let's first define stoichiometry. Stoichiometry is just an area of study that examines the quantities of substances consumed. So, like I said before, we're interested in how much do we need, right? Or how much are we going to make? This is based on the law of conservation of mass, which is, of course, that mass can neither be created nor destroyed. Now, this was based on a lot of what Antoine Lavoisier said, and so if we look at a quote here from him, he says this very eloquently. May we lay it down as an incontestable axiom that in all operations of art and nature, nothing is created. An equal amount of matter exists both before and after the experiment. Upon this principle, the whole art of performing chemical experiments depends. And so that's just a really more eloquent way to say, look, we're not going to create matter. We're not going to destroy matter. It has to come from somewhere. So Antoine Lavoisier was a French chemist. He lived from 1743 to 1794. He was called the father of modern chemistry. And so some of the things he did is he discovered oxygens needed for combustion. So we're going to talk about combustion reactions later. He discovered oxygen is needed for that. He both recognized and named oxygen and hydrogen. He helped construct the metric system, and he wrote the first extensive list of chemicals. Now, he was a chemist as a hobby, though. His profession was basically our equivalent of a tax collector, and that really funded his science. And so during the French Revolution, he was charged with tax fraud, and he was taken to the guillotine. And so it was just, he's really interesting if you read about his life, because later those charges were refuted. But there's a pretty famous quote that runs around that says, in a second we took off the head of a Frenchman who we're not going to recover that knowledge as far as science is concerned for another 100 years. So it's just kind of an interesting rabbit hole if that's something that if you're interested in the history of science. Now, so we're focused on stoichiometry. We're focused on the amount of things we need to make. That means we need to really understand chemical reactions and chemical equations. Now, there's some things that are just a review here, and so just kind of be aware of that, right? We remember that reactants are on this side of the arrow, products are on this side of the arrow. We can now use the names that we learned in the previous chapter. So we see sulfur trioxide reacts with water to form sulfuric acid. You can see the models here that are used. And what we need to remember is that chemical equations must obey the law of conservation of mass. Now, chemical equations basically describe proportions of reactant and products during a chemical reaction, okay? So the reactants here are the substances that are consumed. The products are the things that are produced. We also have different types of reactions. So one of the type of reactions that we're going to talk about are combination reactions, where two or more substances combine to form one product. And so the reaction that you see here is an example of a combination reaction. Now, we can also have something called a decomposition reaction, which I like to think of as the opposite of a combination reaction, where one reactant decomposes into two or more products. And so an example would be when calcium carbonate is heated, it decomposes into calcium oxide and carbon dioxide. And so that would be an example of a decomposition reaction. Now, when we think about reactions, it's important to understand that these describe the changes on an atomic level, and they are going to represent the facts that we know, okay? And so, for example, we know that if you have sulfur trioxide, it reacts with water, it's going to form sulfuric acid. If iron oxide reacts with sulfuric acid, it's going to form water and iron sulfate. I want you to notice that there are letters that follow the chemical compounds here, and they tell us the physical states of the products and reactants. So S is a solid, L is a liquid, G is a gas, and A is aqueous, and that just means it's mixed with water. So it's not fully a liquid, it's mixed with water in some way. Now we're going to look at balancing reactions later in the chapter. What we're going to look at right now, though, is the mole. So the mole is a unit for a specific quantity of substance. A lot of times it's called the chemist's dozen, for example. So, for example, we know 1 dozen of something equals 12 units. So if I say, hey, look, we have 1 dozen atoms, you would say, great, Dr. Pierce, we know you've got 12 atoms, right? If I say we've got 1 dozen elephants, you'd go, great, I know we have 12 elephants, okay? If I were to use, for example, a gross, 1 gross, that equals 144 items. So if I said, hey, look, I have a gross of atoms, you say, hey, I know that's 144 atoms. If I say I have a gross of elephants, you say, hey, look, I know that's 144 elephants. We can do the same thing with a mole. And so 1 mole is just another term for a large amount of something. And that amount is 6.022 times 10 to the 23rd items. Okay? Now, what that means here is if you have 1 mole, then we'd say, hey, look, you have 6.02 times 10 to the 23 atoms. If you've got 1 mole of elephants, you're going to have 6.02 times 10 to the 23 elephants, right? So we call this Avogadro's number. This was named after Amadeus Avogadro, and we'll talk more about him in the gas law chapter. And it is based on the number of atoms in exactly 12 grams of carbon 12. And so that's where this mole comes from. And so we say, hey, look, there's 6.02 times 10 to the 23rd atoms per 1 mole. And that's Avogadro's number. Now, when we look at this, just like if we had 6.02 times 10 to the 23 atoms, or 6.02 times 10 to the 23 elephants, we know that one of those is much larger than the other. And so this image is showing us some differences and different amounts of things that are representative of 1 mole. So this would be 1 mole of carbon. This is 1 mole of sulfur. That's 1 mole of mercury, 1 mole of copper. And then this is a mole of gas. Okay. And so we use this to help us express these macroscopic quantities that are involved in chemical reactions. So we can also use the mole as a conversion factor. Now, to convert between the number of particles and a mole, right? So you would say, look, here's the number of particles. There's 6.02 times 2 times 10 to the 23rd particles per mole. That'll give you the number of moles. If you start with the number of moles, just like any conversion factor, we can flip-flop the two, and now we're going to cancel out moles here, and you end up with number of particles. And so this can help us with atoms, molecules, photons, any sort of thing used as a conversion factor. Now, there's another conversion factor we will also use, and that's called molar mass. And so molar mass is just the mass in grams equal to the mass of an individual atom or molecule. Now, what you're going to see is a lot of times this is shown as AMU, which is atomic mass units, or we can show it as grams per mole, right? So those can be the 2 units there. So this is the mass in grams of 1 mole of a substance. So for example, 1 atom of helium equals 4.003 atomic mass units. So we use atomic mass units when we're talking about atoms. If we're talking about 1 mole of helium, right? And remember, 1 mole of helium is 6.02 times 10 to the 23 atoms. That's 4.003 grams. And so then we say the molar mass, and the unit, the symbol for molar mass is a kind of cursive M, of helium is 4.003 grams per mole. Now you can also see this out here for sulfur, right? So we say, look, this is the molecular mass of sulfur trioxide. It's 80.06. And sometimes you'll see a U here per molecule. You can see the mass of 1 mole, right, which is 80.06 grams. And then the molar mass here is 80.06 grams per mole. So we find these on the periodic table underneath each individual element. Now, I want to talk a little bit more about molecular mass. So we talked about molar mass. I want to talk a little bit more about molecular mass. Molecular mass is just the mass of 1 molecule of a molecular compound. Okay, and so the sum of the atomic masses of the atoms that are in that compound is how you get the molecular mass. So if you add up all the atomic masses, you will get the molecular mass. Now, and so that's what we saw with sulfur trioxide on the previous slide, SO3. We took and we would add the atomic mass of sulfur, the atomic mass of 3 oxygens. We add those up, and we get 80.06, right, grams per mole. That's what we see there, or U per molecule, depending on what you're using. Now, we can also see, and what we've seen more in chemistry more recently, is formula mass. Formula mass is the mass in atomic mass units of one formula unit of an ionic compound. Okay, so this is come out in where we say, look, if it's covalent, then it's a molecule, and we are going to determine the molecular mass. If it is ionic, we are going to call it a formula mass, but we determine these in the same way. So, for example, sodium chloride is ionic. We would figure out the formula mass for that. That's 58.43 grams per mole, because we took the molar mass of sodium, we took the molar mass of chlorine, we added the two together. And so that's what we see there. I want to do one other example of molecular mass just to make sure we're all on the same page. For example, if you needed to calculate the molecular mass of CO2, what you would do is you would say, hey, look, I have carbon, and I know looking at the periodic table, the molar mass of carbon is 12.01 AMU, and I'm going to add the molar mass of oxygen, but see, with that subscript there, I have two oxygens, so I need to multiply that by 2. So 2 times 16 AMU, that equals 44.01 AMU, right? Now, we could also say, look, that's 44.01 grams per mole. I'm going to be really honest, we're going to use grams per mole more than anything else. And so that's really going to become second nature as far as the unit that we use for molecular mass and formula mass. Now, as you can imagine, we can use the molar mass, which is shown here with this little cursive M, right? So that's the molar mass, to convert from grams to moles, right? And so we can convert from grams to moles or moles to grams, but I also want you to notice that we can go then and add this to what we learned about Avogadro's number, and convert from moles to particles, right? So let's look at an example of how to do this. And I have some examples here for you. So now, if it skipped a little bit there, I had to pause it for just a second. You've not missed anything, so we're just going to keep on going. Let's look at this example. The active ingredient in an antacid tablet is calcium carbonate, and some of the tablets contain 0.400 grams of calcium as calcium 2+ ions. How many moles of calcium are in each tablet? Now, what I like to do when I see a word problem is to take as many words out as possible. So I'm going to come here and I'm going to say, look, I have 0.400 grams of calcium 2+, and I am asked for moles. And so I like to write this there. Then I like to think about what I'm going to do. I say, hey, look, I need to convert from grams to moles. And I like to say, okay, what conversion factor do I need here to go from grams to moles? Well, I need that molar mass, okay, which I have a cursive M there. Understand sometimes I'm going to use a double M because I'm old and that's what I learned. So we're going to set this up and say, okay, great. I have 0.400 grams of calcium 2+, and I need to put the molar mass here, and I need to use the molar mass in such a way that the grams are here and the moles are here, so that my grams will cancel out and I'll be left with moles, which is what I'm looking for here. Now, you're going to notice there's a +2. That's because this calcium has lost 2 electrons. Electrons don't weigh very much, so that doesn't affect the molar mass in any way. So we can just go, great, that's 40.078 grams per mole. Now in your calculator, you're going to take 0.400 grams and you're going to divide it by 40. You're going to see your grams cancel out there and you're left with moles, which is what we're looking for. And we had 3 significant figures starting, so 0.00998 moles of calcium 2 plus. We should also have 3 significant figures in our answer. So we had 3 significant figures here, and now we have 3 significant figures here. So there's our answer. Now, let's do some more examples. How many moles of calcium are in 5 grams of calcium? This is really, really similar to the previous one. So if you want to pause the screencast and work this, then you can work it on your own and then check your work. So I'm going to give you that opportunity now. So just hit pause, find your periodic table in your calculator, work this problem, and then you can start the screencast back. Okay, so hopefully you did all that. And we're going to start again. How many moles of calcium are in 5 grams of calcium? So we're going to come here and I'm going to say, hey, look, I've got 5 grams of calcium. And this is not charged. We don't see a 2 plus or anything along that lines. And then it's asking for the number of moles. And so I say, okay, hey, look, I need to go from grams to moles. And to do this, I know I'm going to use the molar mass. Now, we've already looked up the molar mass of calcium. We know it's 5 grams. And again, we're going to put grams here on the bottom, 40.078 grams per mole. And we're going to divide 5 divided by 40.078, and you should get in your calculator 0.124767. Now understand, you need to round that to where it's just 3 significant figures. So these would be 3 significant figures. We're going to look at that 7 there, and we see that we need to round that up. And that's going to give us 0.125, and I forgot the moles there, moles. So we do still need to remember our significant figure rules here. So let's do another example. How many grams of iron are in 3.75 moles of iron? So I'm going to write down, hey, look, I have 3.75 moles of iron, and I'm asked for how many grams. So I need to go from grams to moles. And again, I know I'm going to use the molar mass there. So I start with the number I'm given, which is 3.75 moles of iron. And now I'm going to come here and I'm going to use the molar mass of iron. So I look up at my periodic table and I notice that the molar mass is 55.845 grams per mole. Now I know that mole needs to be in my denominator here so that it will cancel out. So that's 55.845 grams per mole. And we see here that our moles cancel and we're left with grams. So instead of dividing, what you're going to do here then is multiply. And so when you multiply, you should get 209.4185 grams. But understand, we need to round. We have 3 significant figures here in the number that was given to us. So our answer also has to have 3 significant figures. So we look at this number here, that's a 4. That means we're going to stay where we are. We're not going to round up. And so the answer is 209 grams. And so that's our answer for this problem. Well, let's do another example. So in this example it says, how many atoms of sulfur are in 4 grams of sulfur? So we have 4 grams and we're asked for atoms. Now, we can't go directly from grams to atoms, but what we can do is say, look, I know that I can go from grams to moles using the molar mass, and then I know I can go from moles to atoms using Avogadro's number. Okay, and so we're going to do like a 2-step conversion. So we're going to start with grams. That's 4 grams. We're going to come here and we're going to say, great. We're going to convert from grams to moles. This is sulfur. And so I say, hey, look, I have 32.0 0.065 grams of sulfur in 1 mole of sulfur. And then, so I've done that part. I can check that off. So now I'm here at moles because my grams have canceled out, and I need to go from moles to atoms. And so I'm going to come here and I'm going to say, great, I know I need to use Avogadro's number. I know Avogadro's number is 6.02 times 10 to the 23rd atoms per mole of sulfur. And so we can see here where the mole cancels out, the sulfur doesn't cancel out, the moles cancel out. We're still using sulfur here. And so what I would do in my calculator is I would put 4, I would divide by 32.065, and then multiply by 6.02 times 10 to the 23rd. When you do this, you should get 7.5097 times 10 to the 22nd atoms. But again, remember, we need to think about significant figures. We have 2 significant figures here, so we need to have 2 significant figures here. So we're going to look at this number right here. That's a 0, so we're going to stay as is, and we should end up with 7.5 times 10 to the 22nd atoms. And so that's our answer. Now, I'd like to do one more example where we're looking at the molecular weight or the molar mass. And so this problem reads, calculate the number of moles of glucose in 5.380 grams of C6H12O6. So in this, we know we have 5.380 grams, and we're looking for the moles, and it's C6H12O6. And so we have another piece of information we need to figure out, but we need to calculate it. We need to figure out the molar mass of glucose. So to do this, we say, okay, look, I know I have 6 carbon atoms. So for carbon, 6 times 12.011 grams per mole equals 72.066. For hydrogen, there's 12 hydrogens, so 12 times 1.0079 grams per mole equals 12.0948. And then for oxygen, there's 6 of them times 15.999 grams per mole. And so when you look at that, that's 95.994. When you add all these things up together, we get 180.1548 grams per mole. You can use this entire thing, but you can also round. You need to round to at least 2 decimal places for all your molar masses. So, for example, I'm going to use 180.15 grams per mole. Do not go less than 2, okay, because that'll give you some rounding errors. So, we start with 5.380 grams. We come here with our molar mass, and that's 180.15 grams per mole. And that gives us, we take 5.380, we divide by 180.15, that gives us 0.029864002, and we need to round. And so we look here, and the problem gives us 4 significant figures. We ignore the molar mass when we are thinking about significant figures. And so we come here and say, okay, those are the 4 significant figures. I need to look at this one to round. That's less than 5, so it's going to be 0.02986 moles. And that is going to be our answer. So we have in this screencast talked about moles and Avogadro's number. And what we are going to do now in the next screencast is look at balancing chemical reactions.